Hello everyone and welcome. Today we're diving into something really special, a truly groundbreaking discovery in organic chemistry that feels like it's straight out of science fiction. We're talking about building complex molecules using basically just sunlight and air. So let's get into how they pulled it off.
I mean, just think about that question for a second. It's a pretty powerful idea, right? For years, this has been one of the holy grails of green chemistry. The dream is to make all the important things we need, but without all the harsh chemicals, crazy high temperatures, and nasty waste. Well, this research takes a massive leap in that direction.
So, here's our roadmap for today. We're going to start with a really tough chemical puzzle. Then we'll meet the two catalysts that team up to solve it and discover the absolutely ingenious self-powering reaction they figured out. After that, we'll look at the proof, peek under the hood to see how it works, and wrap up by talking about why this is such a game changer for chemistry.
All right, so every great scientific story starts with a big, hairy problem. And in our case, that problem is a chemical bond that is notoriously strong, stable, and frankly, just doesn't like to react.
The bond we're up against is the carbon-hydrogen bond on what's called an sp³ carbon. All you need to know is that this carbon atom is already super stable and content. It's bonded to 4 other things. It's chemically happy. Trying to break that bond is kind of like trying to get your friend who is perfectly comfortable on the couch to suddenly get up and run a marathon. You know, it's going to take some serious convincing.
Now, it's not like chemists haven't been able to do this before. We have ways. But those methods, well, they're often the definition of brute force. We're talking harsh chemicals, blasting reactions with heat, and using expensive, often toxic metals. It gets the job done, sure, but it's like using a sledgehammer to crack a walnut. It works, but it's messy and creates a ton of waste.
So, to find a smarter way, the researchers turned to a couple of really powerful tools from the modern chemist's toolkit. On their own, each one is impressive, but put them together, that's when things get really exciting.
So, in one corner, we have N-heterocyclic carbenes, or NHCs. These little guys are masters of a trick called unpoling reactivity. The best way to think about it is that they can take a molecule's chemical personality and just flip it on its head, making it do reactions it would never dream of doing otherwise. And in the other corner, we have visible light photocatalysis, which is pretty much what it sounds like, using ordinary light as a clean, gentle energy source to kick off reactions at room temperature.
Okay, so you might think you just mix these two things together and you're done. But here's where the researchers had a truly brilliant insight. Instead of just following the standard recipe, they came up with a much more elegant hypothesis.
This quote from the paper says it all. They thought, wait a second, what if we could get rid of the external photocatalyst entirely? Their big idea was that the starting materials themselves could react to form a new molecule right there in the flask that would absorb the sunlight and then drive the whole process. The reaction would literally power itself.
And this is where they knew they were onto something. You see, based on what was known, they expected to get one simple product, which you see up top in reaction A. But what they actually got, down in reaction B, was something way more interesting and complex. The reaction did 2 amazing things at once. It broke that tough CH bond, and it built a whole new molecule. This surprise was the aha moment that told them their crazy idea might actually be right.
This diagram shows that brilliant idea in action. You don't need to add a separate light-absorbing molecule. The starting materials themselves get together and create one on the fly, what chemists call an in situ species. And that species is what absorbs the sunlight, gets all energized, and then powers the whole catalytic cycle. It's incredible. The reaction literally brings its own solar panel to the party.
So, a beautiful hypothesis is one thing, but in science, you've got to have the receipts. You need cold, hard evidence. So the next step was to run a series of clever experiments to prove this self-powering idea was really what was happening.
And this table tells a story that's impossible to argue with. They ran the reaction, but each time they took away one crucial ingredient. Run it in the dark? Nothing. Remove the oxygen from the air? Zilch. Take out that NHC catalyst? Again, no product. The conclusion is crystal clear. You absolutely need all 3, the light, the oxygen, and the NHC. All of them are non-negotiable.
But this next experiment, this is my favorite. It's just so elegant. They'd have the reaction running, soaking up light, and then they'd just put it in a dark box. And bam, the reaction would stop, dead in its tracks. But the second they put it back in the light, it would fire right back up again. This is the smoking gun. It proves that light isn't just helping, it's the literal on-off switch for the whole show. So, the final test. Is this a one-trick pony, or is it actually a useful tool? Well, they tested it with a whole bunch of different starting molecules, tweaking this and that, and as you can see from all those percentages, it worked beautifully almost every single time, giving them really good yields. This proves it's a robust, versatile method that chemists can actually use.
Okay, so we know it works. We've seen the proof. Now it's time for the really fun part. Let's pop the hood and take a look at the elegant molecular machine that makes this whole thing go.
The whole amazing process really boils down to 4 key steps. First, activation. The starting materials team up to form that special light-sensitive molecule. Second, light absorption. That molecule, called a Breslow intermediate, soaks up a photon of sunlight and gets all energized. Third, transformation. That energy drives a whole cascade of events, including the key step where that unbreakable bond is finally broken. And fourth, the final product. Oxygen from the air comes in, finishes the job, and releases our brand new molecule, getting the catalyst ready to go for another round.
And here it is, the whole shebang, the full proposed mechanism in all its glory. Now, I know it looks complicated, but you can actually trace the 4 steps we just talked about. It's just this perfect, self-sustaining loop, a beautiful molecular dance where all the partners know their moves, all powered by nothing more than a light.
So we've gone through the problem, the solution, and even the nitty-gritty mechanism. But now let's zoom out and talk about the big picture. Why is this discovery such a big deal?
Well, because this is pretty much a picture of what the future of chemistry should look like. I mean, just look at this checklist. It's totally metal-free. The energy source is sunlight. Doesn't get more renewable than that. The main chemical oxidant is just oxygen from the air we breathe. It's lower waste because it powers itself, and it all happens at room temperature. It's a blueprint for a cleaner, smarter, more sustainable way to make things.
And this isn't just a nice idea. The numbers totally back it up. These are green chemistry metrics, and they tell a fantastic story. An atom economy over 83%, that's really high, meaning very few atoms are wasted. And an E factor of just over 4, that means for every kilogram of product, you're only making about 4 kilograms of waste, which is incredibly low for this kind of chemistry. The data is clear. This method is ridiculously efficient.
But for me, this might be the most important number of all, 79%. That's the yield they got when they scaled the reaction up to make a whole gram of product. That proves this isn't just a cool trick that works on a tiny scale. It's robust and practical enough to be a genuinely useful tool for making real amounts of chemicals.
So we end right back where we started, with a process that takes light and air and uses them to do incredible chemistry that used to be incredibly wasteful. It just makes you wonder, if they can solve this problem so elegantly, what other impossible reactions are just waiting out there to be reinvented? What else can we build using the clean, abundant resources that are all around us? And that question is what makes the future of chemistry so exciting.